Every tree on Earth is doing roughly the same thing. It's capturing sunlight, pulling carbon dioxide from the air, moving water upward against gravity, and staying structurally intact long enough to reproduce. And yet, forests look radically different depending on where you are. Some trees grow tall and straight, some spread wide, some form narrow cones, others barely grow leaves at all. This variation isn't decoration. It's not random creativity. It's the result of the same physical rules producing different solutions under different constraints. Before we go further, it helps to clarify the lens we're using here. These aren't formal biological categories. They're functional groupings, or ways of organizing the organisms by their main structural constraint. You've seen this idea before. Think of the fin on a whale fish and a penguin. They all look remarkably similar, but they aren't that closely related. One's a mammal, one's a fish, and one's a bird. They converge on the same shape because they're all trying to solve the same physical problem, moving efficiently through water. In biology, this pattern is called convergent evolution, and in this video, we're going to apply that same way of thinking to trees. Strategy 1. The vertical competitor. In a dense forest, sunlight is scarce near the ground. The limiting factor isn't water or temperature, it's access to light. When many organisms are competing for the same vertical resource, the system rewards height. Trees in these environments invest heavily in upward growth. A strong central trunk, minimal lower branching, flexible wood that bends rather than snaps in the wind. Lower branches often die off entirely. Shaded leaves cost more energy than they return. From a physics perspective, this is an optimization problem. Maximize height per unit of structural mass without buckling under gravity or wind load. This is why trees like redwoods, firs, and pines grow tall and narrow. In crowded systems, height becomes access. Strategy 2. The canopy spreader. Now, change the environment. Imagine open woodlands or savannas, where sunlight is abundant and competition is lower. Here, growing taller doesn't provide much advantage. Instead, the limiting factors shift. Wind loading, mechanical stability, structural support. Trees in these environments spread outward rather than upward. They develop wide branching angles, broad horizontal crowns, and thick trunks to handle bending forces. The goal isn't height, it's surface area. From a structural standpoint, these trees are building large, stable platforms for light capture. Oaks and acacias are classic examples. When light is plentiful, coverage beats height. Strategy 3. The load shedder. Now move into cold or high latitude environments. From here, the main threat isn't competition, it's accumulation. Snow creates enormous downward force. If it builds up on branches, failure is inevitable. So these trees don't try to support the load. They avoid it. These trees' conical geometry allows snow to slide off. Downward angled branches prevent buildup, and needle-like leaves reduce surface area. This is not about strength, it's about geometry. The safest load is one that never accumulates. Spruces and firs don't look triangular by accident. They are shaped by repeated exposure to gravity plus snowfall. Strategy 4. The resource conserver. Finally, consider dry or nutrient-poor environments. Here, sunlight is abundant, but water is scarce. The governing equation changes completely. In these systems, losing water is more dangerous than missing light. So, trees use some of these strategies. Smaller or seasonal leaves, thick bark or photosynthetic stems, or deep or extensive root systems. Some species reduce leaf area drastically, and others move photosynthesis into the trunk itself. The goal is no longer about maximum intake, it's about minimum loss. Mesquite, palo verde, and olive trees are all classic examples of this. In constrained systems, efficiency dominates expansion. Before we close, just one important clarification. Trees aren't just solving one problem at a time. Most species balance multiple constraints simultaneously, and those constraints can shift as a tree grows or as local conditions change. What we've looked at here are dominant pressures, not rigid biological categories. That simplification doesn't distort what's happening, it just helps make the structure more visible. Evolution doesn't search for perfect forms, it produces viable ones, constrained by physics, materials, and environment. What looks like biodiversity is often physics made visible. So the next time you see a tree, don't ask, what is this called? Ask, what constraint is this structure solving? I'm Alex Warden. Thanks for watching.